Colloquium. So today we have as a speaker for our Colloquium Christophe Grojean from DESY, and I'm going to introduce a little bit our speaker. So he got his PhD in 1999 in Saclay, right? After that, he had a career all around the world. He was a postdoc in Berkeley. Then he moved back to Saclay. Then he was a visiting professor in Michigan, right, for a few years. And then he moved to CERN, where he still is associated right now. Then in 2012, he moved to Barcelona as a research professor. And in 2014 or 15, there is a bit of doubt about that, he moved to DESY. We don't remember anymore. We moved to DESY, where he is right now. So he's an expert on various topics in particle physics beyond the standard model, like the Higgs boson and possible incarnation in various theories behind and so on. But today he's going to talk about future circular collider, what, why, and when. So please, okay. The floor is yours.
Thanks a lot. So it's a pleasure today to tell you about the future, right? So we'll move forward maybe 20, 30 years away from now. And I want to discuss what we are going to do with this machine. So why this is actually an interesting and exciting project. So here you have a drawing actually of of the LHE, this little tunnel of 27 kilometers. And this is the project that we are going to discuss, the Future Circular Collider. So what is it? So it's a versatile particle collider housed in a 91, 92 kilometer underground, about 200 meter on average underground, right? And it will be implemented in several stages, similar to what happened with LEP and LHC. So the first one is actually colliding electron and positron to produce many Higgs boson, many Z boson, to study flavor, QCD, the top quarks, right? And that's what we call FCC-EE. And then later on, it will be followed again by a hadron collider. So you will place the electron and the positron by proton, reaching an energy scale of maybe 100 TeV, maybe 120 TeV, if you have enough powerful magnet. We still don't know exactly what the magnet will be. There is a lot of R&D going on this side, but the goal is to reach basically 100 TeV and maybe a little bit more. So that's what is called the FCC-HH collider. So what I want to tell you today is first, why do we need a new collider at all, right? And then I will present the FCC feasibility study that is going on at the moment at CERN. It started a few years ago. It's supposed to end sometimes next year with the conclusion whether or not this project is actually feasible technically, feasible financially, and feasible also physics-wise, whether it's interesting to do it or not. So I will tell you a little bit about the study that is going on. And then, I think most of you are actually physicists, so what we care about is what this machine can do, and I will briefly present the physics case of this collider. I will insist on the fact that, first of all, it's really a Higgs and electric factory, right? So you will produce and study with high accuracy the Higgs boson and all the electric sector. But I will also show you that actually this machine will be the best flavor machine, the best flavor factory that you can imagine. And then I will briefly discuss the exploration at the high energy frontier with FCC-HH. And I will insist on the complementarity and synergy between those two colliders. Okay, so why do we need a new collider, right? People are saying, well, you have discovered the Higgs boson. There is nothing else to discover in particle physics. I think we need a new collider because LHE has been very successful, because it has been a fantastic machine that made great discovery. This Higgs boson is a great discovery. We'll come back to that in a moment. And this allows us to formulate new questions. New question that the current collider cannot really answer, and I will give you example of question that LHE cannot address. And clearly, we want to understand better what is the structure of space-time, the structure of matter at smaller and smaller distances. So yes, what is really the legacy of the LHE? So that the standard model has been confirmed to very high accuracy up to energy of several of TeV, let's say. And that was not given from the beginning. I mean, LHC at the end turned out to be a very precise machine also. It has been sold at the beginning as just a discovery machine and exploration, but actually it has achieved really some extraordinary precision measurement. For instance, the mass of the Higgs boson now is known to the per mil level, right? So the fact that the LHC is also a precision machine, really came as not a surprise, but really as an endeavor, so a large effort from all the communities, the experimental and theoretical community, that really give firm control of all the experimental and theoretical systematic uncertainty. So as you all know, the Higgs boson has been discovered with a mass exactly predicted within the standard model by the measurement of, let's say, of electric precision measurement performed at LEP and, I don't know, at SLD in SLAC also, right? But the other big discovery is that actually nothing else was discovered, right? I mean, the absence of discovering a new particle is on its own also a big discovery. I mean, I have some friend like Gavin Salam that said that the biggest discovery of the LHC is that supersymmetry was not discovered, right? And it's true. I mean, discovering that things don't exist is important. It is important to make progress and to move ahead. But in particular, the fact that there is no new physics where everybody was expecting that new physics will be discovered in the TV scale means that the traditional new physics model, like supersymmetry among them, or maybe Technicolor, those models are somehow in trouble, right? So it means that you need to think differently, to think out of the box maybe, or rethink about the main problem. And this rethinking, lead to new approaches, in particular to the hierarchy problem, to understand why the weak scale is separated probably from the scale of new physics later on. So there is new approach like that. I mean, the relaxion model, end naturalness, or clockwork, maybe some of the models that I will describe in the next 2 lectures at the school, are interesting approach in the sense that they use the interplay between cosmology and particle physics to really bring the vacuum of the standard model to the vacuum that we know, the vacuum that breaks electric symmetry with a mass of the Higgs at 125. Previously people were thinking that this vacuum is set only by particle physics, by the dynamics of the various fields, in the vacuum, etc. But now, I mean, people have realized that actually there could be a nice interplay between particle physics and cosmology. That's why you should follow all the lecture by Kfir, right? So that's new approaches, and certainly we want to learn a little bit more, probe those kind of models, right? So indeed, I mean, the main conclusion is that the TV scale naturalness agent, like the stop, in supersymmetry, or I don't know, the KK gluon, the KK whatever, KK excitation of the top quark, might, that in principle are there, to stabilize the weak scale. Actually, those agents might not necessarily explain dark matter or baryogenesis, etc. In the past, we thought, we are going to solve the hierarchy problem, and then automatically all the problem in nature will be solved. We will find a candidate for dark matter. We will know exactly how this imbalance between matter and antimatter is generated. Well, now people have understood that that may be not necessarily be the case, that you have to, to think differently. And as I say, cosmology might play an important role. So the current situation really calls for a broad, versatile, and ambitious program that at the same time will sharpen our knowledge of already known and discovered physics. I mean, you want to measure with very high accuracy all the particles that exist in nature. And from that, maybe you will learn that things don't exactly fit according to the prediction of the standard model. But you also certainly want to push the frontier of the unknown at high scale and at low scale, right? The fact that cosmology might play an important role means that maybe, new physics can be very light and very weakly coupled. Maybe there is an axion and things like that. So you need also a machine that is able to probe not only the TV scale, but also this light and weakly coupled sector, so this elusive sector. And I think really together, FCC and EE and HH really combine these two aspects. They provide more precision and more energy to bring more sensitivity to new physics. So I want to spend some time, really to explain to you that precision is also a discovery tool. And there are various examples, from the past that you can invoke to illustrate this point. Maybe from the 17th century, by doing some precision measurement in astrophysics or whatever, stellar physics, or planetary physics, you could discover actually new planets, right? For instance, Le Verrier looked at some anomalous trajectory of Uranus, and from that he concluded that there could be a new planet that explains actually why this Uranus trajectory doesn't really obey the prediction of Newton mechanics, right? So clearly he say, well, there is a planet that I haven't seen yet, but there should exist a planet there at this particular point with this particular mass, and this will explain this peculiar trajectory of Uranus. And then he sent a letter to his colleague, to this experimentalist colleague in Berlin, that at that time had the best telescope, right? And indeed, they looked exactly where Le Verrier predicted, and they found this Uranus, right? This Neptune, sorry, they found Neptune. So, that's a great, that was a great time, where you make the prediction, and 3 days later, you were able to get a confirmation, right? So I'm a little bit jealous because now, we can make some prediction, and the project that we are discussing takes 30, 40 years, right? But you have to be patient. That's okay. So yeah, so sometimes, by precision measurement, you can discover new planet or new particles. But sometimes, you can also discover new fundamental laws of nature. And that's exactly what happened with this anomalous trajectory of Mercury, right? Again, Mercury is a planet orbiting around, the closest planet orbiting around the sun. So it's turning quite rapidly. So you have a lot of luminosity. You can do a lot of measurement. And there, clearly, again, this trajectory were not in adequation with the prediction of Newtonian mechanics. So Le Verrier said, oh, I found the solution, it worked well for Neptune, so I can imagine that there is a new planet that will also explain why Mercury trajectory is anomalous. So he did all his computation. Again, he sent a letter to his friend, in Berlin. They looked at it, and this time they couldn't find anything, right? Of course, you all know that it took a few more years until Einstein arrived and finally understood really what is going on. There is a new notion of space-time. You have to abandon Newtonian mechanics. You have to think in terms of general relativity, and then everything fits again with experimental data. Right? So again, it's another example where basically precision measurement, lead to major discovery, a new vision of space-time. Closer to particle physics, you could also say that the Higgs boson was discovered indirectly before it has been observed by the LHC, simply by looking at how the Z and W boson interact with the quarks on the lepton. Right? So the only way to make sense of this interaction was indeed to have a Higgs boson, and you could also almost predicted the mass of the Higgs boson. Right? Of course, you can predict it given a theoretical framework. In this case, it was a standard model. Assuming that the standard model is actually what is going on, you know exactly where the Higgs boson is, simply by looking at the interaction of the W and the Z at the quantum level. Right? So these are, fantastic example, I think, where really precision measurement, lead to prediction, or at least lead to discovery. Right? So sometimes it's true that these discoveries were expected based purely on theoretical arguments. You can think of quantum mechanics. There were some inconsistency, in these Rayleigh-Jeans UV catastrophes that really required quantum mechanics. Or the Higgs also is predicted in the sense that without the Higgs boson, the theory becomes ill-defined. So you need a new ingredient, a new degrees of freedom to restore mathematical consistency to your theory. Nonetheless, it's true that precision always gave valuable additional data in addition to theory. And in any case, I think experimentalists shouldn't lean too heavily on theoretical prejudices prejudices, so they shouldn't listen too much to theorists. If you can do an experiment, if you can achieve high accuracy, you should do your experiment and go ahead, right? Don't listen too much to what the theorists will tell you they will discover. You will discover, right? And in any times is really a time when we don't have a precise theoretical guidance, that we need really powerful experimental tools to make progress further on. Right? Sorry, wrong button. Yeah, it is. Okay. So the FCC project really offers an unprecedented opportunities on many different fronts. So it's true that we are not, in the same situation as before the LHE, where we knew that we will discover something. There was this no-lose theorem that basically just looking at the behavior, or I don't know, or the weak interaction, you have a mass scale where you are sure to discover something, right? Either the Higgs boson or something else, something that should replace the Higgs boson, again, to ensure the mathematical consistency of the theory. So we don't have, at the moment, a no-lose theorem. Nonetheless, there is a promise to actually make significant step forward in our understanding of the fundamental understanding of nature, right? Again, not discovering anything is still learning something about nature, right? So it's not because, your condensed matter friends are telling you, you are not going to discover anything, that you shouldn't do your experiment. I mean, again, we are really probing something that have never been probed before. We don't know the structure of matter. We don't know the structure of space-time at distances shorter than 10 to minus 20 centimeter. Maybe you have some theoretical prejudice about how it should be, but we are doing physics, so it's an experimental science, and we should do and check what is really going on. Right? And that's really what FCC can do. So there is certainly, one sector, one particle, whatever, that requires precision, is the Higgs boson. So it's true that the Higgs isn't everything, right? The Higgs is actually everything. Sorry. Okay, wrong button. Yeah. So the Higgs isn't everything, it's the only thing, right? So the scalar discovery in 2012 has made an important milestone, has been an important milestone for high energy physics. Many of us, including myself, are still excited about it. I think many of you are excited about Higgs physics, and I think everybody else should be excited about the Higgs, right? And there are very reasons for that. First of all, because the Higgs boson really is associated to new forces that are of totally different nature compared to the other fundamental interaction that we have learned at school, right? The weak, the electromagnetism, the strong interaction are based on gauge theories. So they are associated to local symmetries. As far as we know, this is not the case for the Higgs boson. It is not associated with any gauge symmetry. First of all, furthermore, those interactions, those new forces are not quantized. The electric charge is quantized, is always proportional to the electric charge of the electron. This is not the case, apparently, of the interaction of the Higgs. The interaction of the Higgs with the quarks and the lepton can be arbitrary. It's a continuous parameter, basically. It can take arbitrary value. And also, what is really fascinating is that those forces are actually deeply connected to the vacuum structure of space-time. Is precisely because, the space-time break SU2, the vacuum of space-time break SU2 cross U1 down to U1 of electromagnetism, right? That those X forces emerge, right? Those Yukawa interaction between the Higgs and the quarks and the lepton are there only because you have electric symmetry breaking. So the discovery of the Higgs opened new deep question. What is the origin of the Higgs boson itself? I mean, it's the first scalar particle that is ever observed in nature, right? And there are good reasons, to believe that it's very rare to actually find a scalar with a mass which is not the Planck's mass, right? Because the radiative correction of any scalar potential, push the scale of the scalar to very high energy, to the highest energy scale that you have at your disposal, unless you have particular mechanism to screen this quantum mechanical effect, right? So you can ask yourself whether actually the Higgs is indeed an elementary particle, right? Whether it's not a pion, I mean, not made of two new technique works, right? Whether there is the new bond state of a new force with new fundamental interactions. So that's something we want to understand. We also want to understand which role did the Higgs play during the Big Bang, and how did it influence the evolution of the universe afterwards, right? Whether, for instance, the Higgs played any role during the inflation of the universe. Right? There are scenarios about that, but nice theoretical model, but again, it's just theoretical model. You want experimental data to really understand what happened, right? And we want to understand whether the Higgs boson also play a role in explaining all the fundamental open questions in particle physics, which the standard model cannot address. I mean, the problem of flavor, why the muon at the end of the day is different than the electron, right? What makes those two particles different from each other? As far as we know, it's only their interaction with the Higgs boson. So are those interactions totally arbitrary, or whether there is actually a deep physical principle behind it, right? There is, of course, dark matter. As you know, I mean, the standard model does not provide any good candidate for dark matter. So maybe it has something to do with the Higgs. The Higgs could be a portal to a dark matter sector. Baryogenesis, inflation, etc., etc. So all these questions, require physics beyond the standard model. So we know that physics beyond the standard model exists. We don't know what it is, but maybe the Higgs, will help us to really understand, right? Or will serve as a portal. Right? But also, I think it's important to understand that really we need to know with high accuracy the value of the Higgs coupling to matter, because it really dictates the structure, the deep structure of matter and the deep structure of the universe, right? So we know, for instance, that the mass of the W and the Z are responsible for the lifetime of stars. The sun is burning since several billion of years because the mass of the W and the Z is of the order of 100 GeV. Right? If those masses were close to zero, the sun wouldn't shine at all. Right? By the way, it's also interesting to notice that the lifetime of star, right, is very similar to the time that life need actually to evolve. Right? So it's maybe a coincidence problem, but it's quite fascinating to think that maybe life exists at the end of the day because of those masses, and those masses exist because of their interaction with the Higgs boson. Right? So that's something that has been established, I think, with good accuracy already at the LHC. Right? We know for sure, I think, at the moment that the mass of the W and the mass of the Z are connected to the Higgs coupling. So that's something very deep that we have learned. But there are also similar questions, that at the moment remain purely theoretical hypotheses, right? Think of the mass of the electron, right? So the mass of the electron is super important because the mass of the electron determines the size of the atom, right? Remember this Bohr radius. The Bohr radius involves the mass of the electron. So you change the mass of the electron, you change the size of the atoms, you change the size of all the objects, right? Change the size of the universe, maybe. Whether or not, the mass of the electron really originate from its interaction with the Higgs boson at the moment is a purely theoretical hypothesis. Right? We have no experimental evidence that the mass of the electron is linked to its interaction with the Higgs boson. So that's something we would like to establish for sure. Right? It's also true for the mass, let's say, of hadronic matter, right? So it's true that the mass of all matter has nothing to do really with the Higgs, right? I mean, mass of the proton is mostly QCD, strong interactions. Nonetheless, it's important that the Higgs interact with the quark that are inside the proton and the neutron, right? Why is it important? Well, because QCD, is isospin invariant. So QCD doesn't see the difference between the up and the down. So for QCD, the proton is equivalent to a neutron. So the QCD contribution to the mass will be exactly the same for the proton and the neutron. Of course, up and down quark, are slightly different. They have different electric charge. So you have a contribution to the mass that is coming from QED, from the interaction with the photon, that will make the difference between the mass of the proton and the mass of the neutron. But in this case, QED will actually give a larger mass to the proton compared to the neutron. So if you have only QED and QCD, you expect that the proton is heavier than the neutron, and then the proton will decay. Right? So this means that no nuclei will be stable. So it's only because the up quark has a mass which is slightly lighter than the down quark, and because the proton is 2 up quark and 1 down quark, while the neutron is just the opposite, so 2 down quark and 1 up quark. At the end, is only because of this tiny mass difference between the up and the down that the proton is lighter than the neutron, and that nuclei are stable. But the pending question is where the mass of the up and the down is coming from. Have they anything to do with the interaction with the Higgs boson? Of course, most theorists, will think it is the case, right? I mean, it works so well for the top quark, for the bottom, for the tau leptons, right? Why should we believe that this is not true also for the electron, for the up and the down? Well, that's also what happened, when people were believing that the weak interaction were respecting parity. There were no reason to believe that that the weak interaction don't respect parity, because the electromagnetism respect parity, gravity respect parity. So why not the weak interaction also? But there have been an experiment. I mean, Mrs. Wu looked at how those big nuclei of cobalt decay, so how they were dying. And at the end of the day, she noticed that parity is maximally violated in the weak interaction. Right? So this is, I think, a great example where when you can do an experiment, you should do it, right, irrespectively of what the theorists are telling you. So I think it's really important also that we get a clear confirmation whether or not the masses of the electron, the up and the down, have anything to do with Higgs interaction or not. Another important question is actually what took place in the universe 0.1 nanosecond after the Big Bang, at the time where the universe gets filled with this Higgs substance, right? Where the Higgs substance, the Higgs expectation value really filled all the universe. Right? It's a dramatic event, right? I mean, the universe saved a lot of energy by doing that. Right? I mean, the energy density, between these two minima of the Higgs potential correspond basically to the energy of the sun inside the container, right? So that's the amount of energy that you can save, that the universe saves. But nobody exactly know what happened exactly at that time, right? So we know that this phase transition took place, but we don't know the dynamics. And there is no picture, no movies at that time. I mean, because there were no photon, right? I mean, you cannot take a picture. At that time, there were no photon. And this dynamics of this phase transition is actually controlled by the Higgs potential. So whether it's a first-order phase transition, a second-order phase transition, it depends mostly on the Higgs potential. I mean, there is all this thermal correction, etc. But what is really important is the zero temperature potential of the Higgs. And maybe it's not only a Higgs, maybe there is also all the scalars. I mean, maybe there is some singlet, etc. Actually, if you want to have a first-order phase transition, most likely you will need additional scalar field. Right? So that's something we need to go and measure again, this Higgs potential, to maybe understand really what took place in the universe at the very early moment after the Big Bang. And then there is also this question of imbalance between matter and antimatter. So you need a new source of CP violation, and maybe the Higgs interaction can provide actually a lot of new source of CP violation. In the standard model, the only source of CP violation that we know is precisely the interaction of the Higgs with the quark and the lepton via this famous phase of the Kabibo-Kobayashi-Maskawa matrix. But this phase is not large enough, or more precisely, the effect of CP violation is not large enough to explain the imbalance that we see between matter and antimatter. So we need new source of CP violation. And clearly, we need to measure all the interaction of the Higgs boson to see whether or not we have additional source of CP violation. This is not the only option. I mean, maybe there is new particles, there is the axion. Why not? The axion might also violate CP, explain the strong CP, but it can itself has source of CP violation. But certainly the X is a good source of CP violation, and we want to check whether it exists or not. Right? So certainly the LHC and high luminosity LHC will also do it later, will, provide valuable information, but certainly won't be enough to really answer this kind of question. And we need a new collider to answer this important question about ourselves, about matter, about the universe. Right? So that's why we need the X factory. So what is this feasibility study that is going on at CERN? I think it's a result of the last European strategy for particle physics, that took place 2019, 2020. The conclusion, and has been shared later on by the NOMAS process. Laura can tell you a little bit more about that. But the conclusion is really that we need an electron-positron X factory that is highest priority in order to understand the Higgs boson. And later on, maybe this first machine should be complemented by another machine, a proton-proton collider, to reach very high energy, maybe to reach this 100 TeV energy scale. Right? So that was the conclusion, the recommendation of the physics community. And the CERN Council, which is the deciding, the governing body of CERN, approve this strategy, say yes, makes sense, let's do it. And then the CERN management, so it means the CERN DG basically, is in charge of implement this strategy. So as a result, this feasibility study was launched in 2021. It will be completed, as I said, next year in 2025, right? And we had a midterm review in 2023 to see, whether it makes sense to continue or not. Sorry? Yeah, it passed. Well, midterm, it was, last year, it was presented in February. And then the question is whether it makes sense to continue this feasibility study or not, right? I can tell you the political reason of this midterm review, but not publicly. So what was the objective of this feasibility study? So first of all, it was to demonstrate whether it's really feasible to construct such a machine geologically, right? You need a place where you want to put the machine. You cannot send the collider in space yet, maybe in the future, but at the moment you want a collider on Earth, and you want to see whether it fits really near CERN or near Geneva, right? Whether, you can build it technically, right? Whether you have all the infrastructure or whatever, the technical aspect, but also all the environmental aspect. Whether, for instance, you don't need to burn, a lot of coal or whatever to produce the energy which is needed to run these machines, right? Whether you are not going to destroy all the nice forest or mountains around Geneva to make sure to run your machine. Right? The second aspect was really, a purely administrative aspect. You want to make sure that France and France and Switzerland agree to have this machine on their soil, right? At the end of the day, there are many people living in this area. You cannot do whatever you want. Okay, CERN is an international organization. He has some land. On this land, he can do more or less whatever he wants, but it doesn't fit really on CERN ground. So you need to go beyond the CERN land, and you need to get the authorization to do what you want to achieve. Another important question is, of course, also the budget, right? The operational cost. You want to make sure that you have enough money, not only to build the machine, but later on to operate this machine. So you need, people to sit down together and estimate the cost to construct this machine and later on to run it. And you need a plan, to go to your prime minister or your funding agency to say, well, I would like a few more billions, right? Give it to me and I will build these machines. So all these aspects have to be discussed, and you need to have a plan. And this plan will be proposed to the CERN Council, and the CERN Council will give the approval or not. Go ahead or stop the project. Doesn't make sense. And of course, you also wanted to understand why actually it makes sense to build this project from the scientific point of view, right? What kind of answer you expect, what kind of measurement you expect, what kind of sensitivity you expect in the measurement of all the X couplings. Right? So the first question was exactly where to put this tunnel, right? So at the end of the day, you want a tunnel which is close to 100 kilometers, but there is a lot of constraint. I mean, I don't know if you know Geneva, but here there is the Jura mountain. Somewhere over there, there is the Alps. Here you have the Lake Geneva. You have a lot of cities around. So where to put this tunnel was really not obvious. And also you want to optimize various things. I mean, for instance, you don't want, to put the tunnel in a place where there is no road to access this tunnel, right? I mean, you need to bring people, not only to construct the machine, but also to operate the machine later on, right? So how much kilometer of road will you have to build? How much new electricity line you need to build to provide the energy to the machine? So there is certainly an optimization process, an optimization program to really to really see and figure it out what is the best location of this machine. So at the end, there were more than 100 initial variants of this layout of the tunnel that was considered. Various things have been optimized, the consumption of electricity, consumption of water, etc. And it has been nowadays finalized with this drawing, right? Yes. So this is, the various communes, whatever the various villages where the tunnel will pass by. And now, you need to go and discuss with the mayor, with the people that are living in these communes, maybe with few people that have some houses there that will have to be destroyed somehow yes, that's all the aspect that you have to think, if you want to make this project happen, right? So all this green area is the communes where there have been discussion now, and the yellow one is the one where the discussion are planned and will happen in the next few weeks or few months. This plot is probably outdated anyway, so everything should be more or less green at the moment, right? And now another important aspect is also, what is actually the structure of the rock behind you, right? Because you want to dig your tunnel 200 meters down. So you want to make sure, for instance, that there is no water. When you will build your tunnel, when you will dig the tunnel, it will be a catastrophe to find a lot of water. It will be very difficult to build something when there is water around. You want also to understand what is the structure of the rocks, right? Whether you need this type or the other type of boring machine. So there is a lot of studies that are going on at the moment. If you walk around CERN, you will find this kind of experiment going on. So these are just drilling machines that are there to really understand the structure of the rock up to 200 or maybe 400 meters below you, right? Similar drilling tests are going on actually under the lake. So the tunnel, as you see here, the tunnel will go below Lake Geneva, right? But you want to understand exactly, what the structure of the rock below the lake. By the way, when I say, that it's not trivial where to place this ring, because if you go too far in that direction, for instance, Lake Geneva becomes more and more deep, and then it will require to dig far deeper to build the tunnel. So you are limited, basically you are limited in this region where Lake Geneva is still shallow enough, and you can put your tunnels there. So all these aspects, are really highly non-trivial. And that's something that took place in the last few years, and now more or less everything is really ready. There is a good understanding of the structure of the rock and what will be needed to dig the tunnel. Right? Another aspect is actually what are you going to do with the material that you will excavate, when digging the tunnel? It's something like 8 million cubic meter of soil, right, that will be extracted from the earth. And nobody wants this big pile of earth in their garden, right, clearly. So you need to understand what you are going to do with that. And there are various ideas, actually, how to, to use this excavated material. For instance, usually it's mostly rocks, right? So you cannot do much of it, except that there is some ideas, for instance, to put some fungi to make this rock fertile, right? So you can use this soil actually to grow some plants or to grow some forest, right? So there are some experiments at the moment that are going on in that direction to really to use this excavated material. There is also the problem of heat. You know, when you will be running this machine, you will, produce a lot of heat. What are you going to do with this heat, right? So there is some projects clearly to use the heat, clearly to heat the local houses, to the local schools, whatever. But there is also some project, for instance, to use it for some cheese factories, right? They need some heat, and it's very interesting because in the Jura and Haute-Savoie, clearly there is a special interest for that, right? And there are some contracts that are being made, people are discussing this. Also to have some friend supporting the project, clearly. Now the other aspect that I was mentioning is how to construct the road, right? First of all, to bring the material, to bring out the excavated material, or to bring people that will go down to run the experiment. And with this particular layout of the tunnel, it was concluded that you need to construct less than 4 new departmental roads to really access all the points in the tunnel, right? So it doesn't mean that you need to do a lot of infrastructure. Most of them is already there, existing. It's only marginal addition that you need to do. The same is also true for electricity grid. Whether you can really bring all the electricity that you need. I will mention later on. The amount of energy is a few terawatt hour per year. So it's a consumption of a big city like Geneva that you need to run this machine later on at the end of the day. But it's not trivial. Whether or not you want to build, for instance, a power plant just to provide enough energy to run this machine, or whether you can rely on the existing electricity grid. And clearly, you don't want also to disturb too much the existing electricity grid, right? So you don't want that the people in the nearby cities complain when you turn on the machines, right? So all this aspect has been studied, and was confirmed that basically you can do it without problems, right? And then the question is precisely how to dig the tunnel, right? This 100-kilometer tunnel, basically, 200 meter on average underground. So the way you will do it is via these tunnel boring machines. So you will have, at the end of the day, you will have 4 experimental points, right? There is 4 interaction points where you will collide the beam. But you also need 4 additional shafts, where whatever for the RF or for the collimation of the beam, etc. So at the end of the day, you have 8 experimental points, right? 4 where you will have some experiment and 4 that are technical things, right? So these shafts will be used basically to bring down the tunnel boring machines. Those tunnel boring machines, they will progress at a rate of 18 meters per day. Right? That's a good machine already. There is not so many of them available. At the moment, I think there is only one factory that can produce those boring machines. It's somewhere in China, as you can imagine. But okay. So it will take about 8 years actually to dig the tunnel, right? So this is the structure of the rock. So somewhere here, here there is Lake Geneva. So you go under the lake, and you see that most of the rock has actually a structure that you like. It's called molasse. It's very easy to dig in molasse. In other pieces, these pieces, for instance, there is a bit of limestone. Limestone are more difficult to make things stable, so it's more difficult to dig there. But this is a place that you couldn't avoid. But certainly you want to minimize the amount of limestone that you will encounter when digging this tunnel. Right? Clearly, it's not a flat tunnel. It's not horizontal. First of all, when you're talking about something of 100 kilometers, you have to take into account that the Earth is not flat. Right? Maybe the biggest result of FCC is a demonstration that the Earth is not flat. Right? People will be convinced at the end of the day. So, but anyway, it's not horizontal, so the tunnel is slightly tilted, and is tilted indeed, to maximize basically this digging into molasse. Right? And this is the schedule of civil engineering. When you dig, how far you can progress in the tunnel, etc. So it's a very tight schedule, clearly, but people are hoping really to manage to dig the tunnel, to have everything ready by 2040. But yeah, it's non-trivial, right? Also because there are things that you cannot process in parallel, right? I mean, you need to dig, and so you need a clear plan what you will do and then what you do next, etc. Right? And that's this nice Excel sheet that people are working on at the moment. Right? You can try to zoom in at some point. Yeah, the resolution of the screen is not good enough. Right? So this feasibility study at the end culminated for the moment in this midterm report that was presented at the CERN Council last February. So it's a 700-page document. There are 7 chapters. The cost and financial feasibility aspect is a separate document. It's highly sensitive, so nobody wants it to be public. So there are 7 chapters, a placement scenario, so where you put the tunnel, so you wanted to discuss exactly your conclusion, the civil engineering aspect, implementation with the host state, the technical infrastructure, the design of the collider and performance, the accelerator of FCC-HH, and then finally physics and experiment, which is the last chapter. You always want to conclude with physics. So of course, nobody is able to read the 700 pages document. So CERN Council also asked to provide an executive summary. So it's a 44 pages document. But again, nobody has enough time to read the 44 pages document. Right? In principle, in particular, nobody in the CERN Council, which are very busy people, can read a 40-page document. So they ask, subcommittee, review this and make us a summary, right? So there is a scientific advisory committee at CERN on the cost review panel that met sometimes in October. The scientific policy committee and financial committee at CERN met in November, and the CERN Council finally received all these documents and were happy, right? February 2nd, they all met, they reviewed these documents and say, okay, you have done some good work, you can continue. Yes. So you can download, if you have a CERN account, you can download this midterm report and read it and enjoy it and fall asleep at night. Right? So let me tell you a little bit more. Time is running fast. I don't know. There is 44 pages, and I'm only at slide 15. Okay, I'm talking too much. So let me tell you a little bit about the content of the physics part, right? That I was most directly involved with. I mean, people wanted us to write 60 pages, but at the end of the day, we had a lot of things to say, so we provided 110 pages. First question was, what are the specificities of the FCC physics case? What are the theoretical calculations that you need to perform to be able to exploit all the data that you will collect, right? Because, I mean, at the end of the day, you need to interpret the data. To interpret the data, you need to compare with a standard model prediction, for instance, or to compare with the prediction of various scenarios of physics beyond the standard model. So you need theories to do these things, right? And that there are many things that are not available at the moment, not even the tools that are needed to perform those calculations are available. So you need the plan to plan ahead. And then another very important question is, what are the detectors that you want to build? What are the characteristics of the detector in order to achieve the measurement that you want to do? So whether you want, I don't know, a detector like Atlas, a detector like CMS, like LHCb, like ALICE, all these kind of things. You want to really need to figure it out what are the characteristics of the detectors in order to achieve the sensitivity. Because you will produce 1 million of Higgs boson. You will produce 10 to the 12 or 10 to the 13 Z boson. So the statistical uncertainty will be of the order of 10 to minus 6, for instance. But that's a statistical uncertainty. You need also to make sure that all the experimental uncertainty, all the systematic uncertainty are under control at this level of precision. And for that, you need, fantastic, for instance, momentum resolution or tracker resolution or particle ID, right? So you need to understand what are the characteristics of your detector to really keep all the systematic uncertainty under control. And then, of course, there is 2 more sections about overview and outlook and whatever, conclusion. So at the end of the day, many people read this report and they were all happy. Even the financial committee, say, well, you should think about the physics no matter how much it costs. You know, just focus about the physics, tell us what you need, and we'll make sure to provide the money. Okay, they are not the guy that will provide the money at the end of the day. So, but I mean, it's still. I mean, the president council say it's the first time I've heard, you know, the financial committee say, don't think about the money, don't care about the money. And we had even, I mean, you know, the French president and the Swiss president that visited CERN in November. That was really a big success for Fabiola Gianotti, the director. She wanted to bring them to CERN, you know, to have a commitment on their side to say, well, look at how important this project is. Also, I mean, not only for science, but also for technology, right? It's important because those projects will develop technology that will be useful later on, I don't know, to run your car or to run your cell phone or whatever. And, you know, Europe and the Western world should keep some leadership and don't leave everything go to China for these kind of things. That's why, I mean, all the presidents are interested in this project. They don't care about the Higgs boson, but they care about, you know, the technological aspect that will be developed in order to build this tunnel. Also, in the US side, I mean, there have been some interest. I mean, in April, CNDG went to the US, went to the White House. They signed together an important statement of intent saying that the US will contribute, you know, once the project is approved by the CERN Council. They really are interested in contributing financially, but also in terms of human resources. Right? So it's a nice picture in the White House. Right? So what is the time scale? Right? I mean, the conclusion that you should have in mind is that we are only 20 years away from the first collision. Right? So what is 20 years? Right? So I asked my kids. And they had these nice tools, you know, that can project you in the future. So this is now. This is what will happen in 20 years from now. Right? Okay, but there is a lot of things to do in between. Right? So the expression of interest, you know, from the detector community are expected in 2025. There will be a conceptual design report expected in 2031, a technical design report in 2035. Installation inside the tunnel. So the tunnel will be dig, everything will be ready. You can install your accelerator, your detector inside in 2041, and you have the commission of the machine in 2045. Right? So that's a clear plan that has been approved by the CERN management now. So things are actually moving a little bit faster than anticipated. For instance, you know, the European strategy update that was planned 26, 27 has already moved forward by 1 year. So, you know, there is good hope and you can feel younger, right? So what is the organization of the project at the moment? So there are various pillars: physics, experiment detector, accelerator, technical infrastructure, and then, I don't know, people that I don't talk that often, but I meet once every 2 weeks, you know, all state processes and civil engineering, organization, and financial models, right? So it's many people, but conclusion is that there is actually many opportunities to engage. You should get in touch with a working group convener, you know, either you're interested in physics, whether you're interested in detector, in building some detector. Yeah, everybody is welcome to join. Physics performance, software and computing, EPOL, machine detector interface, everything you need, really. I mean, it's not a single man, a single physicist can build this machine. It's really together, putting a lot of expertise together that will make this project feasible, right? Okay. So in the last 5 minutes, I will give you a very quick overview of the physics. So what are the characteristics of this machine? So the important thing of a circular collider, so here clearly we are talking about circular collider, is the behavior of the luminosity, so the amount of collision that you can expect as a function of the center of mass energy. Right? And for a circular collider, this luminosity decreases with the energy. While for a linear collider, it's usually just the opposite. You know, the luminosity will increase with the energy. And actually, the two lines will meet at energy around 350 GeV, 500 GeV. That's the point where basically, you know, if you want to go above those energy, it's better to construct a linear collider. But below this energy, is much more advantageous to build a circular collider because the luminosity is much higher. And what is really fantastic here is to look at the luminosity that you can collect at the Z-pole. Right? For FCCEE, it is expected basically to produce something like 10 to the 12 or 10 to the 13 Z boson. So LEP, that was a fantastic machine, produced 10 to the 7 Z boson. Right? So FCCEE will repeat LEP experiment in every minute, every 2 minutes. So it's not so much that you have new accelerating technology, whatever. It's simply because the machine is much more performant, right? You have improved all your technology by 4 or 5 orders of magnitude in 30 years. Right? That's really a fantastic machine. So what are we going to do? So clearly here, you want to run the machine at the Z-pole to understand with higher accuracy what LEP has already discovered. You want also to run the machine when you are able to produce a pairs of W boson, so at 100, let's say 160 GeV. Then it's an X factory, so you want to produce the X boson. And if you look at the production cross-section of the X boson at E plus E minus collider, there is a peak at 240 GeV. The cross-section is maximal at 240 GeV. So certainly here, you want to run the machine at 240 GeV to produce something like 1 or 2 million of X boson. By the way, the LHE has produced something like 8 million of X boson, right? So it's not that you are going to produce so many more X boson than the LHE. But here, it's an E plus E minus machine, so you can see every X boson that you are producing. Something that you cannot do at the LHE. You have signal, but the signal is really buried under a huge background, and it's only about one over 1,000 that you can see at X boson that you can see at the LHE. So at the end of the day, you produce 8 million of X boson, but you can observe about 1,000 of them only. Right? So here is again 3 orders of magnitude larger than what LHE has achieved and will achieve until the end. Right? And then finally, you can also reach the TT bar threshold, so at 260 GeV or so, to produce the top quark with a high rate. Right? So in each detector, you will produce 10 to the 5 Z boson every second, 10 to the 4 W every hour, and about 1,500 X boson per day and 1,500 top quark per day also. Right? And again, if you have 10 to the 13 Z boson, so you expect a statistical uncertainty of 1 over square root of 10 to the 13, so it's about 10 to minus 6. So there are some challenges to really control all your uncertainty at this level. And you need really a combination of various aspects. So theoretical calculation, clearly, I've already mentioned. You need to develop some Monte Carlo, right? You need to develop lattice simulation, because at the end of the day, it's E plus E minus, but there will be a lot of QCD also. So you need also to do some lattice simulation. There is software and computing, how to do some simulation that are large enough to model 10 to the 13 Z boson. And certainly this detector requirement, detector concept, control analysis, all these things are really challenges that you have to think ahead if you want to exploit all this data. So let me give you a snapshot of what we are going to do with FCCEE. So as I say, there is 3 main aspects. There is the X, right? So you want to study the X, to measure the mass of the X, the X width, to measure with high accuracy all the X coupling, in particular the X-self coupling. There is a top quark. The top was discovered at Tevatron, but there is a lot of things still to understand about the top. And finally, what is really unique about FCCEE is this 10 to the 12 or 10 to the 13 Z boson that you will be producing. This is the intensity frontier machine. Of course, there is nice intersection or correlation among these 3 aspects. But why is it so interesting to produce 10 to the 13 Z boson? Because first of all, you will do fantastic electric and QCD measurement, right, with an accuracy which is far higher than what you can do at what was achieved at LEP. You will also learn about QCD, the fragmentation function, etc. That's something that you can measure at FCC, at the Z pole. And then, you will be able also to directly search for light new physics, because you are producing so many Z bosons, you can be sensitive to very rare decay mode of the Z. Right? And this is the case, for instance, if you have axion-like particle, dark photon, or heavy neutral lepton, or long-lived particle. That's the kind of object, that you don't observe if you have only few events. But you have so many events, then you will become sensitive, and then you can really probe the parameter space of all this kind of exotic model. But again, it's interesting because, maybe the solution to the hierarchy problem is really coming from this elusive sector, which are light and weakly coupled. Right? So that's why it's interesting to have a Z factory in addition to the X factory. Right? Something that we might have totally missed at LEP, now you will become sensitive when you have 10 to the 12 Z boson. And then it's also a fantastic flavor factories, because all these Z boson will decay into B quark or charm quark or into tau leptons. So you will produce 10 to the 12 pairs of BB bar or CC bar, so 10 to the 12 B mesons. So many tau that you can really achieve tau physics. You can check universality of the weak interaction in the tau sector. Right? You can do a lot of measurement about the tau lifetime, etc. That flavor factory cannot do, simply because here you have many more events, and also you have those events in a kinematically interesting region, because here the B quark or the charm quark that you are producing are coming from the decays of the Z boson. So these are objects that are highly boosted compared to what is happening in the flavor factory, where you are producing those objects on shell. So here, those objects are boosted, and this gives you, a lot of freedom to reconstruct various things, right? So this is nice advantages of this flavor factory in the highly boosted regime. But of course, you can do this only if you have the right detectors to do your measurement. So for instance, if you're interested in long-lived particle or axion-like particle, you better have a good detector hermeticity. You want to make sure that nothing escapes your detector. You need also good tracking or good calorimetry. If you want to do flavor, clearly you need high momentum resolution. You need a good tracker. You need a good verticing, or tagging energy resolution, hadron identification. So these kind of things are really being quantified at the moment. Really, what are the characteristics of the detector that you need to achieve this measurement? Right? So these are some examples of the performance of the detector that you need. Right? So this is another plot that shows the physics program of FCC. So there are 4 main runs at the Z pole, WW, ZH, and TT bar. Right? But there are also other opportunities. For instance, you can run the machine at 125. So 125 is the magic number, right? It's the mass of the Higgs boson. So it means that you can collide an electron and a positron to produce directly the Higgs boson as a S-channel resonance. And that's where you want to access the electron Yukawa. Right? By really measuring the production rate of the Higgs boson by colliding an electron and a positron at 125. Is a challenge. Is a challenge because the Higgs is a very narrow resonance. There's a resonance, a width of 4 MeV. So you need to control with high accuracy the energy of the beam. And there are other challenges, etc. But that's a very interesting opportunities we need to access a fundamental quantity of the standard model, which no other machine can do. You can also run below the Z pole, where it's very useful if you want to do some QCD precision studies, in particular the fragmentation function. But now you will have also this nice accelerator, and there are opportunities also, to do physics differently. You can use the electron from the injector for beam dump experiment. You can extract the electron beams from the booster, or you can reuse the synchrotron radiation photon. So this FCC can be actually the best light source on Earth, right? Of course, We are not so much interested in all this aspect, but different community might be interested in having a machine like that. Right? So you can explain to us, you can explain to them why it's also interesting to build FCC if you want to do photon science. Right? Okay, so now I see that my time is running over. Maybe I can jump to the conclusion. You can look at the slide later on if you want, and we can discuss, ask me some details. Many things, and many things that you can do. Okay, so conclusion and outlook. A circular X factory like FCCEE has a rich potential to search directly and indirectly for new physics, right? It's important to have a machine that can explore the energy frontier, but also a machine that can explore this intensity frontier, the Z and whatever is below the Z. FCCEE is an essential part of an integrated program, and there is some guaranteed deliverable, but also a broad exploration potential. So we have certainly profound questions, and we need to create opportunities to answer them, and certainly FCC will contribute there. So colliders are the most powerful microscope we have to study nature at the smaller scale, at the smallest distances, and also to learn about the very early moment of the universe. And they certainly keep providing a quantitative understanding to make progress forward. Right? So we need a new collider, clearly. Thanks.
Okay, thanks a lot for... Okay, we have already questions there.
Of course. Hi, Grojean, thanks for the talk. So, I'm Thiago Tomé, I'm part of the SMS collaboration. So first, let me thank you for the talk. And disclaimer, I'm very interested in this project going forward for very obvious reasons, because I want to work on this. However, I think it's part of my job to poke holes in the proposal, so I'm going to be extremely provocative here.
Welcome.
First, I fully agree with the fact that we have to have a new collider, and I fully agree that exploring the Higgs boson and having a Terra Z factory is the way forward. Mm-hmm. It's not obvious to me at all that FCC is the right thing. In particular, just after, you might remember that just after the Higgs boson discovery, immediately after that, people were whispering the words Lab 3, and all of that completely disappeared. On the second, and on another hand, it's a bit curious, of course, that CERN is curious, but at the same time it's natural, that CERN is spearheading, because obviously CERN wants to build a new collider, because there is no big project after high luminosity LHC. So it's kind of asking, hey, do you want to work more on this project? Of course CERN will answer yes. And the fact that things are already moving forward, as you have shown, and again, I am interested in them moving forward, it's fait accompli. FCC is going to happen. But how are we going to defend, given these kinds of pointed questions that we will for sure receive? Thanks.
Sure. About Lab 3, I mean, it's not that people have forgotten about Lab 3. I mean, there have been some studies around it, and there are various reasons why actually Lab 3 is not as good at FCCE. But first, there is the technical reason, is that if you want to reach the energy that is needed, you need to add ARF cavities. And the tunnel of the LHC tunnel is not large enough to fit actually the machine there. So it's just a technical issue. You will need to enlarge the tunnel of LHC to fit the machine inside. There is another aspect, which is a time scale simply. You cannot go dismantle LHC before the end of high luminosity LHC. And even you have to wait, because this many point of the LHC will be very hot, very radioactive. So you have to wait. So it means that there is a huge delay between the end of high luminosity LHC and the beginning of Lab 3. So it's not that Lab 3 will arrive before FCCE, just the opposite. Actually, FCCE can be ready much earlier than Lab 3. And then, I think for me, Lab 3 is a sort of dead end. You will do your measurement with the X, but then what's next, right? FCC has the potential, to go on beyond that high energy with HH. There's also technical challenges, how to develop all these magnets, etc. That, at the end of the day, if you want to convince a politician, you need to show that there are some, spin-off in technology, and FCC-HH has this component that Lab 3 doesn't have, right? So there are various aspects. I mean, we can, of course, discuss about the physics. The luminosity at Lab 3 won't be as large at FCC, clearly. But yeah, we have answer to this kind of criticism, clearly.
Yeah. I was wondering about the low coupling light extra degrees of freedom. So naively, as a complete outsider, I would expect that by increasing the energy, you would you would bury this signal more and more under the sea of other signals. So is there a smart way to undig those
Well,
signals?
I mean, this is the case at proton-proton collider, but not at electron-positron, right? At the end, I mean, the signal of the background is of order 1 at the E plus E minus colliders. So that's why you are very sensitive to what is happening at low energy.
So when you increase the statistics, then you will have more.
Yes. I mean, why, for instance, FCC-HH is also X factory, right? I mean, I mentioned that FCC-EE produced 1 million of X boson. So why do we want to continue to do X physics at FCC-HH? Because FCC-HH will produce something like, 10 to the 10, 10 to the 11 X boson. So you will become sensitive to very rare decay mode of the X boson that FCC-E cannot do it. So the two machines are complementary in that sense, if you are only interested in X physics. But there is also exploration potential, I don't know, of supersymmetry, whatever. You can see that you will gain, in fact, 1 order of magnitude easily compared to LHC, simply by increase of the energy, by increase of the rates.
Okay. Thank you for the talk. I really liked it. It was very thorough. I was wondering, I really like that sustainability is like a thing that you have in mind. But I noticed that you are taking care of the residues and the byproducts that you produce. But I was wondering if you also are taking care of the input that you put in. So, for example, if you're going to visit the site 10 times, are you going to take 10 planes? Or if you have to make detectors, are you going to use recycled metal and all that sort of stuff? Is that a thing for you?
These are concerns, that you need to document clearly in this feasibility study. This is an important aspect. Yeah. So the operational cost, I mean, in terms of money, but also in terms of carbon footprint, right? Yes. And that's one good aspect. You can compute, for instance, the amount of carbon dioxide that you emit per X that you are producing, right? I have tables, I think, in the supplemental. Yeah. Okay, we can check. There is some table that really show the comparison of the amount of carbon, the carbon footprint of a circular collider compared to linear collider. I think I want to show it to you because that's interesting. It's true that the linear collider people are telling you, well, you use less energy because you don't radiate. I mean, in a circular machine, you have radiation because the electron, the beam is circulating. So you're losing energy. But the luminosity, I mean, you don't lose the beam, right? So you can use the beam. What is it? I have a plot that shows the amount. It's probably one of the last plots. Here, right? You can see here the amount of energy consumption per X that you are producing, right? And you see that FCC is a greener machine. And you have also to take into account that the energy that is used at CERN is mostly energy which is produced by nuclear power plants, so it's green energy, right? Doesn't emit any carbon.
Yes,
so
okay.
All these aspects make FCC a sustainable project. Of course, you're right that there is the transportation of all the people that will be working on this project. This is.
Yeah, because most of the laws right now are aiming to contrarrest the damage that you're making, but not always they care about the things that you're bringing into the project. Sure. So that was my question. If you're trying not to just take care of the trash that you make, but to prevent making any more.
Absolutely.
Thank you.
But the greener machine will be a machine that doesn't run at all, right? So I think, I mean, those machines, I mean, certainly they will have an impact on the environment, on the electricity, etc. But that's a good investment for humanity. You know, you don't want to build this machine to save energy, but to find a way later on to save energy. Right? It's like, I mean, you know, people that develop the lead. I mean, you know, probably they were a cost, you know, to develop this lead. But at the end of the day, afterwards, you have saved a lot of energy. Right? So that's the way science is making progress. Right? It's an investment, yes.
So you mentioned theoretical calculations, but I'm sorry, maybe you didn't get enough time to talk about it. But yes, with the FCC, we'll get much more experimental precision, but theoretical, and they need to be on comparable level.
Absolutely.
So currently, what's their level, and by the time FCC will be operating, will they match? It's harder to calculate these perturbative calculations, right?
They will match if theorists are sitting down and start doing their computation, right? I mean, as I say, the calculations are not available at the moment. The tools are not available, so you need to develop your Monte Carlos. You need to develop, you know, the way to perform, you know, electric correction at 2-loop and 3 loops. People don't know how to do it at the moment. There is a hope that, you know, if everybody is sitting together, you know, spending enough time, enough money in PhDs and postdoc, those computations can be done. But yeah, there is also something to prepare. You know, it will depend on you, and we will need you. You will be the one, you know, running and exploiting those machines.
Okay. Okay. Just about the general construction and general working of mainly the detectors. I imagine there is a lot of background coming from outside the detector that you have to compensate. Is it since the detector is quite big? Is it like location dependent on where your detector is located? Like, for example, LHC, is Atlas and CMS, do they have to compensate differently for the backgrounds? And would this?
No, I mean, first of all, you know, you don't have so many choice where you want to put the detector. As I told you, you know, it's very much constrained already where you put the tunnel. And, you know, you need a four-fold symmetry in order to preserve the stability of the beam. You know, it's not that you can put the two detectors close to each other. Otherwise, the beam will be totally unstable.
Yeah, sure.
So, you know, you need to have these 4 experiments equally spaced along the beam. And basically, there is only one solution. So first of all, there is no big choice. So how much is dependent on the location? I'm not totally sure, but I think anyway, it's, you know, it's really underground and it's shielded from many things. So I don't think it really matters. What matters is more like the characteristic of the detectors themselves, you know.
Okay. And maybe like because we're reaching more higher levels of sensitivity, so maybe at one point this sort of location dependence might be relevant, but it isn't relevant for now.
I mean, they will be relevant. I mean, and the question is to which extent you really have a control on those. I mean, whether, you know, you will be sensitive to a train passing by. LEP has shown that, yeah, you can predict and you can really understand when the train is running, you know, between Geneva and whatever. So, yeah, but it's just a question of whether you can subtract all those effects. And at the moment, people are confident that they can do it. Now, of course, you have to test it in real conditions. Right?
Yeah, okay, thank you.
There, yes. Then we have.
Thank you for the talk. Now, you talked a lot about the performance of the collider itself, but not about the detectors. So you mentioned some performance requirements on the detectors. I would like you to comment a bit on how far we are from meeting those requirements.
You should talk to detector expert. I mean, I cannot talk about the detector performance yet because, you know, we are at the stage where we need to invent those detectors, right? So we need to imagine what kind of detector you need to build. people are confident, it's not too exotic. They can do it. They can achieve it. At least, for FCCE. For FCCHH, it will be another story, because there will be so much radiation and things like that. You need other progress in detector development to achieve the detector for FCCHH. But FCCE, they are not particularly difficult in a sense. But okay, I'm not a detector developer myself, so I don't know.
I have a question, maybe in the same sense of, you said it about you in some part of the presentation about the Tevatron at the top and how LAP was helping on the Z and etc. for new physics. And these proposals are also in the FCC. But if I understand well, in such examples, we saw that they helped a lot. They discovered they had our information for what we are looking for, but then maybe we missed something. We missed something that we could not see in these cases after we saw what we were intended to see. So this is one of my concerns when we are talking about these proposals, because it seems to me that we are missing some lessons. And one of my afraids about FCC, in the sense, is that we did not learn these lessons, and we are proposing them to FCC, and we don't know exactly about the detector, for example. So this is one of my concerns, because LHC, I think, could help us learn these lessons, and we are learning, and I'm wondering if we have enough time to learn these lessons if we hurry up FCC. So this is my question, if I explain myself well.
Yes, I mean, people are learning any lessons, yes. And, of course, there is a big difference between LHC and FCCE. I mean, hadron machines are totally different than electron machines. But and also, I mean, the tools that are available. I mean, yesterday we had some discussion about machine learning. So certainly the way you will do the analysis now are different than the way it was performed at the beginning of LHC. So yes, there have been some progress. Of course, I mean, there is no guarantee that we won't miss anything, but I think we are learning. Yes. But if you have something specific in mind, yeah, let's discuss for sure. Yeah.
Hi, thank you for the lecture. And my question is a little bit more basic. I was wondering, why did they decide to make it circular rather than linear? Because I was thinking about like the precision, right? And we want for example, precision bins to, for example, measure the electron Yukawa. So I was thinking, oh, maybe the linear will be easier to be more precise because the bin will be more controlled, it wouldn't be spinning and...
Luminosity is the key. I mean,
exactly.
Luminosity, to achieve the precision measurement, I don't know, the X coupling to the Z, here at FCC, you will reach a precision of per mil in 3 years, right? You will run at the at the X pole for 3 years, and you will reach 10 to minus 3 precision. To achieve the same sensitivity at a linear collider, you need to run the machine for 30 or 40 years.
Okay. Okay,
right?
fair.
So it's a question of time. I mean,
okay, fair. Thank you.
Of course, if there is new physics, I don't know, at 500 GeV, yeah, a linear collider is much better. But you cannot build a long-term project assuming that there is new physics at 500 GeV. It's not excluded, but there is no indication that this is the case. I mean, this is a regime of energy that the LHE has already explored to a large extent. Of course, there is always caveat, there is loopholes, but there is no indication that there is new physics at 500 GeV. Between 500 GeV and 1 TeV, there is nothing. Maybe. Most likely there is nothing. But yeah, I wouldn't, build a big project to explore this regime with the only hypothesis that maybe, there is one corner of parameter space that the LHE hasn't explored. I want a machine that has guaranteed deliverable, that can achieve legacy measurement that will remain in all the textbook. The way you will study Peskin and Schroeder will be with its FCC measurement later on, right? And then there is exploration potential, yes.
Okay. Are there any more questions? I think no. So there is an announcement, right?
So yes, for people from the school, we're going to have the group picture today, right now. Just wait outside. Don't go for coffee yet, so just wait here, and someone will take a picture of us, and then you can go for coffee. But yes. So
Yeah, now it's time to thank our speaker for this colloquium.